think about that as well. Okay, I will unmute. I'm sure you've got questions now. Okay, Su Ying, any questions?
No, I don't have.
Okay, how about the rest of you? Any questions at all? So far, so good. You gotta warn me if I'm going too fast or there's anything that's not clear. I can go back again. Okay.
Hello.
We are running a little short of time. Yes.
Can you explain a bit more on the z function graph? Like, why must there be a peak to occur?
Okay. So let's say, for example, let's pick this graph here, okay, for prediction. Prediction in yellow and actual in blue. And let me just mute you guys, okay? Okay, so here you've got prediction and actual, and they're lagged, right? Now, remember what the z function does. It fixes the prediction in time. It doesn't change it at all, but it shifts your actuals around, okay? So let's say I shift it right to here. If I shift the blue line right to here on the orange, they completely coincide, right? And so if they completely coincide, according to our formula here, the covariance will be maximum, okay? The dividing by sigma y and sigma y hat is simply just to normalize it, that's all, okay? But as I shift it away, either forward or backward, there will be less correlation between these two graphs. So the covariance here is simply a measure of correlation, agreement. This number is large. When there's not much agreement, this number is much smaller, okay? So that is why your graph often will have a sharp peak, or at least one peak, because there's only one place. If your forecast is nearly or similar to your actuals, that's really where you would have the largest correlation. And if you move it away, then there's less similarity. Everything drops up quite sharply, actually. All right. Okay. Any other questions? One last question from you guys. Because we have to move. It's already 5:54. We are a little behind time today.
Okay, so sorry, just on a question on this lag, right? So I think in reality, we would not see such a very nice graph, right? We would probably see a few different maxima and minima, right?
Yes.
So in those cases, how do we then define what is the appropriate lag, right? Because it's easy to find a local maximum or minimum, but it's not easy to find a global maximum or minimum, right? Across a set of data. Yeah.
Okay, good question. So let me just mute and answer you guys, okay? So yes, you're right. Typically, sometimes there will be spurious maxima or minima on either side, right? They're not very important. If your forecast is anywhere near the ballpark of the actuals, you will always get a single peak and it will stick out like a sore thumb. So in all the practical examples we've worked with for the last many years, it's always been like that. So for most practical data sets, it is like that. If your data is periodic, like a sine curve, for example, let's say any kind of periodicity, then of course you will get multiple peaks corresponding to a shift for the next period. But you just have to look at the near delta equal to 0, and then you're fine. You don't have to consider all the smaller maxima and so on, smaller maxima, smaller peaks. You only want to look at really the largest peak that you have and take that as your lag. Okay? And the sharper this peak is, the more confident you are that the forecast that you're doing, the lag that you're measuring is correct. If this If this peak is very broad, very shallow, then you have much less confidence. Okay, I have to move on. If you have further questions, do ask them in the Telegram group. I will answer them either online or perhaps next week if they are more requires more explanation. Okay, because we are slightly behind time. Okay, so I want to come to my. Let me just move this a bit. Okay, so I want to come to the next thing, which is neural networks, and really explain the kind. There are many kinds of neural networks, okay, and neurons as well. So a neural network is a lot like a house, a brick house. Okay, a brick house is made out of a lot of bricks, and the configuration of the bricks that you use, how you place the bricks, determines the house. You use the same bricks usually, or a few kinds of bricks. So each brick is called a neuron. And how you place the neurons, or how you link them up relative to each other, is what gives your neural network its distinctiveness and makes it different from any other kind of a network. Okay, but essentially, it's like a house with bricks, made out of bricks. The house is your neural network, think of it that way, and the neuron is the brick. And there are many different kinds of bricks that you can use. In this course, we'll be using the simplest possible brick, which is the perceptron. And it was discovered in 1958 by this guy called Rosenblatt. So it's not new technology. But the good thing about the perceptron is that it's very simple, it's very fast, and very useful. Okay. Now, I have to let you guys know that neural networks have been around for a long, long time. So even like CNNs and so on have been around since the 80s, 1980s. It's just that now we have the tools to better train them, more data to train them, etc., more applications, and so on. Okay, but we'll be concentrating on using the perceptron. It's a very simple neuron, and you will be using this to actually do all your forecasting, and it is very versatile. Okay, so what is a perceptron? Well, you can think of it like a blob, or like a machine, if you like. It takes in many inputs, and it spits out one output. So the internal parts of the perceptron is what we call weights. And these weights are just numbers, a list of numbers, which you can adjust. Okay, so let me just flash this a bit more. So let's say I've got as my inputs x1 to xn, x1 to xn. The x's are all scalars. They could be, let's say, the price of Apple stock, could be the volume of a certain stock, or maybe if I'm weather forecasting, it could be, like, say, the reading of temperature, rain gauge, or dew point, etc., and so on, right? They are all different variables. They're scalars, x1 to xn. And the perceptron has got weights w1 to wn corresponding to x1 to xn, and a bias b. Okay, and somehow it combines these things together to produce an output y. Okay, which is a scalar as well, a number. So if you use vector notation, we have an input vector x. The weights are represented by w and b, and the outputs are just a number y. Okay, how is this computation done? Very simply. Well, we first take a dot product between x and w. Okay, that's why the w's must match. If you've got 10 x's coming in, you must have 10 weights in your neuron, 10 w's in your perceptron. And then you add a bias to that. Now, the next step, that part of the perceptron we call a linear combiner. Okay, and it's also very common in things like ARIMA and very simple statistical models. But the distinctive part about the perceptron is that it has a separate nonlinear component called the saturator. It's also known as an activation function. And the idea is that you take that saturator and you apply it to the linear combiner. So essentially, y is just theta of x dot w plus b. Okay, very simple. from a mathematical point of view. Okay. Now, there are many different kinds of saturators. There's a hyperbolic tangent, 10H. It looks like a sigmoid, okay, very similar to sigmoid. The one that we would like to use more often is ReLU, which is 0 below 0. And anything, if your arguments are above 0, it just returns the argument. Okay, that's one. ReLU is not one. Leaky ReLU is very similar to ReLU. It's just that it's got a slight slope at the back of it with an alpha, all right? So it's a slight slope. Now, some pro tips. Now, these tips probably won't make too much sense to you right now. Don't worry about it. Just take it down, bear it in mind. It will become very useful to you perhaps on the second or third day of or third session of this course, okay? The first is that 10H is very slow. So on both CPUs and GPUs. So what are GPUs? They are actually the high-end processors that we use for this course online to actually do the forecasting, do the network training for you, right? So it's slow. No matter how you paint it, it's slow. So always use ReLU as your first option. And use leaky ReLU if you think that you're not getting some good results. You can try something else, all right? And try 10H if you have the time. Oops. And that really is it. So the key takeaway for you is in the kind of style of forecasting that I will teach you in this course, you need to try a lot of different combinations. And in order for you to get an answer quickly, you need to know which choices give you a quick answer. If your training takes, let's say, 10 minutes, that's not too bad. But if you're trying to if you're trying something like 1,000 combinations or 100 combinations, that's a long time for you to wait, right? 100 times 10 is 1,000 minutes, right? It's still a long time for you to wait for an answer. So don't use 10H if you can avoid it. Use ReLU as your first option. It's fast. Okay. Okay, I'm going to open to live discussion. So let's see if we can finish by 8:30. Give me a minute, guys. Let me try and unmute you. Okay, any questions? So far, so good?
No, this session is actually from 7 to 8, so I think we have to wrap up as well.
Okay, no problem. Is it possible for us to do 8:30, guys, or anyone has to rush off? Hello?
I'm okay with that.
Yeah, I'm okay to stay as well.
Okay, so, well, because we had the first intro section, any questions? Okay, no questions, I will go on.